Hello and welcome to our Introduction to JMAG webinar. My name is Dave Farney and I'm in charge of technical sales in North America. I want to thank everyone for attending and I look forward to providing a general overview of JMAG. This is the first webinar in a series of webinars that we're going to try to hold each month to provide information on features in JMAG. This first webinar is more of a general purpose webinar to really introduce JMAG and its electromagnetic platform, but further webinars will involve more in-depth discussions of features such as transformer analysis, machine design analysis, or other tools that JMAG can provide users. I encourage anyone with questions or comments from today to contact your local POWERSYS representative. At the end of the slideshow, we're going to have information both on the office location and contact information for POWERSYS offices across the United States and Europe. During today's webinar, we'll cover four main topics. First, I will provide some background information on how POWERSYS and JSOL are connected to JMAG. I will then go through the JMAG electromagnetic platform and introduce the different JMAG products while providing examples of how these products can be incorporated in your design process. I will then go through examples of how JMAG can provide advantages over other electromagnetic modeling solutions. Lastly, I'll go through some test cases that demonstrate various JMAG tools and functions. First off, JMAG is a finite element analysis software package that is developed by the JSOL Corporation. JSOL is headquartered in Tokyo, Japan, and has more than 1,300 employees. JSOL provides a variety of software solutions across a range of industries, and JMAG is the software solution focused on electromagnetic FEA. JSOL has 65 employees dedicated to JMAG development, and many more that assist in making JMAG what it is. Currently, there are more than 600 separate user sites around the world. Feedback from our users, as well as collaboration with our partners, helps to make JMAG the most powerful analysis tool on the market. JMAG itself was developed more than 30 years ago, so although we are new to Europe and the US, we still have a great deal of experience in electromagnetic FEA. In the 1990s, companies outside of Japan started requesting licenses. In order to better support these users, JSOL enlisted local software distributors. This ensures that sales and support services are delivered quickly and efficiently. JMAG's distributors do more than just sell software. They provide valuable feedback that helps shape the direction of JMAG. The distributor in North America and Europe is POWERSYS. POWERSYS is the exclusive distributor in JMAG since 2006 in Europe and since 2009 in North America. POWERSYS's mission is to engage in business development at the local level and manage the sale of JMAG licenses. This includes both pre- and post-sales support, as well as attending various local events, such as conferences and trade shows. POWERSYS is also committed to delivering the highest quality support for JMAG users and works closely with JSOL to ensure that customers' needs are being met. JMAG is a very powerful tool, and we work closely with our customers to ensure that they can take full advantage of JMAG's capabilities. POWERSYS is committed to each customer's engineering success, and so we strive to understand every customer's individual goals and develop a relationship. Our engineers are experienced JMAG users with a strong background in electromagnetic design and analysis. We believe that we must go further than just answering questions. We must understand our customers' applications so that we can see how each question fits into the larger picture. This means that we can suggest modeling improvements and solve issues more quickly by anticipating what our customers want to do. A powerful FEA package with high-quality support has resulted in a number of companies working with us. Many of these companies are industry leaders, and to maintain this position, they are always working to improve their modeling abilities. Our goal is to take their feedback and develop tools that will extend their modeling capabilities and deliver more information faster. Before discussing the JMAG platform, I would like to mention that much of the information you will see today is available on the JMAG International website at www.jmag-international.com. The website also has application notes section with more than 150 analysis examples. You can also request a trial license for JMAG and find information on upcoming conferences and events that we will be attending. JMAG has multiple products that fit into your design process, from concept creation to detailed analysis. In the next few slides, we'll look at some of these tools and see how they can help you. We like to think of JMAG as a tool that can replicate any measurement that you would take on a test bench. In this example, JMAG can predict motor torque and temperature. Additionally, however, JMAG can provide insight into phenomena that are difficult or impossible to measure directly. For example, you can examine flux density distribution or joule loss distribution in magnets. This virtual approach provides a greater level of understanding of methods that impact devices' performance. JMAG can analyze a variety of applications including rotating and linear machines and generators, actuators, transformers, induction heating elements, sensors, shields, and many other devices. JMAG is primarily an electromagnetic analysis tool, but we also have a built electrostatic, structural, thermal, and multiphysics solver. In the final section of this presentation, we will also see that JMAG can work with many third-party software packages that can significantly build on the internal JMAG multiphysics capabilities. This slide shows a small cross-section of analyses that JMAG can perform. You can see everything from a linear motor on top, to a bus bar on the right, and a magnetic recording head on the left. We can even analyze multi-domain problems such as loudspeakers and induction hardening. The bottom shows a magnetic shield. Effectively, JMAG can analyze any electromagnetic problem up to approximately 1 MHz. All the examples on this slide were taken from our application notes section on the JMAG website, which means that for each of these models you can download the actual JMAG project file, as well as a white paper that goes through how the model is set up and analyzed. If we look at FEA analysis in general terms, each model we analyze can fit somewhere in this continuum. On the x-axis, we have the degree to which the model must be set up, where the left side represents manual setup of the analysis, and the right-hand side represents a more automated approach to setting up the analysis conditions. From left to right, we have an increasingly automated analysis. The y-axis represents the model's complexity, with the bottom part representing a basic model, and the top part representing a more complex model. From top to bottom, we have increasing model complexity. In some cases, the goal is to achieve an automated analysis of a comprehensive model, which would fit into the top right quadrant. But you will probably spend much of your time working in one of the other 3 quadrants. This is why JMAG has products that work effectively in each of the 4 quadrants. When you are first starting the design process, you probably want something that is easy to set up and allows you to quickly iterate on a design. JMAG-Express can accomplish this by offering common motor templates that are easy to set up and can generate basic motor metrics in a few seconds. Once you have narrowed down your design, you can move to JMAG-SuperExpress, which can take the model from JMAG-Express and run a full FEA analysis and pull out the results that are important to you. After that, you can import your motor design to JMAG Designer, where you can analyze more complex phenomena in much more detail. For those of you now working with rotating machines, you will most likely start in JMAG Designer. I should also mention that JMAG Designer does have a transformer template that can simplify geometry creation for transformers. In any case, once you have completed your analysis in Designer, you would probably be done with this project. But what happens for the next project? This is where JMAG Virtual Test Bench comes in. In Virtual Test Bench, you can apply predefined analysis scenarios to a new design. Effectively, JMAG Virtual Test Bench is an analysis template that can be applied to any design to automate the generation of results. All 4 of these products work together and with other third-party software products to really extend the capabilities of JMAG. Another way to look at the JMAG product line is by how each product fits onto the classical V development cycle. JMAG-Express can be used for the initial concept design phase to examine numerous possible design options. Once the number of options has been narrowed down, you can move to JMAG-SuperExpress. Once you are satisfied that a design will meet basic criteria, you can then move to JMAG Designer to perform a comprehensive design evaluation. At any point in this process, you can also generate an RT file to use in a software-in-the-loop simulation for controller development. The RT file is effectively a lookup table that captures your device's performance in a block that can then be exported to any number of third-party software programs. Once you have finished the specification and design phase, you can then move to validation, where you can then start building prototypes. Most likely, you will first start by testing individual components and then finish by testing the complete system. JMAG can also help in validation process with RT files. In this case, you can use the RT file to perform hardware-in-the-loop simulations. For example, if you are developing a motor, you will probably need to develop a controller. Most times a controller prototype will be available before the motor prototypes. Now you can use hardware-in-the-loop simulations to test the physical controller performance by connecting it to a virtual motor. All features of JMAG seek to reduce the amount of time necessary to validate a design. And JMAG itself is also created keeping in mind that there are going to be multiple users of JMAG, from expert to novice users. So you can see that JMAG has multiple products. The internal JMAG products can also work with other software tools to extend your modeling capabilities. For example, when you are creating a geometry, you can use JMAG's built-in geometry editor. However, you can also link directly to CAD packages such as SOLIDWORKS, ProE, and CATIA. Or you can import a neutral file such as a DXF.SAT or IGES geometry. JMAG-Express and SuperExpress have template style setups and can run either a hybrid lumped parameter analysis or run a full FEA analysis. JMAG can also import models directly from Speed. Once the model is in JMAG Designer, you can run an FEA analysis using any of the internal JMAG solver modules, such as transient electromagnetic, structural, thermal, and iron loss. You can also link a model directly to another FEA package, such as Abaqus, Virtual Lab, and AccuSolve. JMAG has a built-in circuit editor, but circuits can also be created in Simulink and PSIM and used to drive the JMAG model. Once you have finished your analysis, JMAG offers a range of post-processing options, including parametric and optimization tools. Optimization can also be controlled by third-party programs such as Optimus and Mode Frontier. JMAG can also export results as a .csv file that can be read into programs such as Excel. As I mentioned in the previous slide, JMAG RT is a tool that can generate a lookup table representing a device's performance. This RT block can be used in circuit analysis programs such as PSIM and Simulink, hardware-in-the-loop programs such as National Instruments, Opal RT, and DSpace, and 1D simulators such as GT Suite and Synopsys Sabre. Okay, so we just covered a lot of general information. As you can see, JMAG has a lot of capabilities. So let's focus on some of the different products. Since machine topologies are fairly consistent, JMAG has tools to help automate model creation. JMAG-Express is a good starting point for most motor designs. It has templates covering common motor topologies such as brushless, brushed, switched reluctance, induction machine, and universal machines. You can also edit any of the templates to create a unique geometry. For example, if your design has fillets on the stator teeth, you can add this feature and create a callout so that you can define that geometry in the Geometry Editor tab. In any case, after you select the machine type, you can set the geometry and analysis conditions with a template style editor. Once you've finished setting the model's conditions, you can hit the light bulb, and JMAG will run a very fast analysis and output basic performance characteristics such as torque versus speed, efficiency versus speed, and motor constant. JMAG-Express is intended for rapid design evaluations. It has a sizing tool that allows you to resize an existing design to a different output power by specifying dimensional constraints. Starting in JMAG version 12, you will also be able to run a sensitivity analysis based on an objective function. You can then see which parameters have the largest effect on your objective. JMAG version 12 will also include an optimization function that can optimize designs based on these objective functions. With the sensitivity and optimization functions in version 12, you should be able to achieve even more with JMAG-Express. Another new feature is JMAG-SuperExpress. We introduced this a couple months ago and have made some big improvements for JMAG version 12. JMAG-SuperExpress works like JMAG-Express, except that the analysis is a full FEA, not just a lumped parameter study. You can set up your model just like in Express, except now you can select a predefined analysis scenario. In the case of this IPM, you can run a back EMF analysis, load analysis, inductance study, or an efficiency map. You can choose the analysis and then set the driving conditions of the analysis. JMAG then runs a full FEA and pulls the results onto a dashboard display. So now you can see all the results in one place. As an example of what SuperExpress can do to reduce your analysis time, let's compare approaches for generating a back EMF analysis at a constant speed in a permanent magnet motor. In the traditional approach, it would require 7 steps. First, creating a geometry and applying the materials. Second, setting the analysis conditions. Third, defining the rotor speed. Fourth, determining the time step. Fifth, set the number of time steps for one electrical cycle. Step 6 is when running the analysis, and step 7 is viewing a graph of the back EMF voltage. In JMAG-SuperExpress, you can accomplish the same thing in 3 steps. First, define the geometry and materials in a template. The next step is selecting the no-load analysis scenario and defining the rotor speed. And the third step is actually just clicking the Run button, and once the analysis finishes, a back EMF graph is automatically displayed in the results dashboard. The traditional approach gives you a lot of control, but requires multiple setup steps, while the SuperExpress approach allows you to select an analysis scenario that will automatically generate the required output. For JMAG version 12, SuperExpress will now work with induction machines to perform drive characteristic analyses, line start analyses, machine parameter characterization, and torque characteristic analysis. JMAG version 12's SuperExpress will also work with switch reluctance machines to perform an ISI characteristic analysis, inductance analysis, torque analysis, and drive property analysis. So we have seen how SuperExpress can reduce the number of steps in setting up an analysis. For most people, every analysis requires a combination of different studies. For example, you see that geometry, materials, and operating range must be set up in order to run different studies and then gather the results from these studies into the desired metrics. JMAG SuperExpress seeks to eliminate setting the internal computations. In other words, you set the input conditions such as geometry, material, and operating range, and then specify which output metric you would like to generate, such as Cogging torque for speed versus torque or efficiency maps. SuperExpress takes care of setting up the individual studies and compiling those results into the metrics that you want to see. This methodology is also what drives Virtual Test Bench. But in this case, now you can apply this process to any device, not just rotating machines. JMAG Virtual Test Bench can take inputs such as geometry, materials, and operating range, and then provide its knowledge to output useful performance metrics. So now, instead of having to set up each individual study, JMAG Virtual Test Bench will run the studies necessary to generate the results that you have requested. Virtual Test Bench has analysis scenarios for a wide range of devices. You can apply these scenarios to your model, and Virtual Test Bench will automatically generate the requested results. Virtual Test Bench includes a scenario library that JSOL will continuously expand, but you can also create your own custom scenarios. JSOL's goal is to have every example in the application notes section available as a scenario in Virtual Test Bench. This can dramatically reduce the analysis setup time and allow you to focus on modeling, not setting repetitive studies. The one product that we haven't looked at today is JMAG Designer. Designer is the core product that all other tools are built from. JMAG Designer is an electromagnetic FEA program that can provide many advantages over other electromagnetic modeling tools. We can summarize JMAG's advantages in 4 main categories: precise analysis, open interface, high-speed processing, and high productivity. The following slides will show examples of features that fit into each of these categories. In order to achieve precise analyses, we must start with a comprehensive material definition. JMAG has an extensive material database with contributions from many top material manufacturers. Magnet manufacturers such as Hitachi and TDK have provided nonlinear magnet properties as a function of temperature, while steel manufacturers such as Nippon Steel have provided electrical steel loss data up to 10,000 Hz. You can also generate your own custom materials as well. By generating comprehensive material definitions, JMAG models can account for magnetizing and demagnetization, high harmonic currents, iron losses, and stress dependency. Precise analyses also requires high-quality mesh. JMAG has its own mesh generator that is highly customizable. JMAG's mesher also has a geometry recognition tool that can reduce mesh noise and eliminate defects in the geometry such as overlapping edges or small voids. JMAG also has features such as the extruded mesh function that can dramatically reduce the number of elements required to accurately model a geometry. In this example, the traditional mesh requires 486,390 elements and takes 71.2 minutes to run. Using the extruded mesh requires only 148,056 elements and takes 16.8 minutes to run. Thus, you get about a 70% reduction in the element count and a 76% reduction in the analysis time. The extruded mesh function also does not sacrifice accuracy, so you achieve both a faster analysis time and achieve a very high accuracy in your results. Another JMAG advantage is its open interface. This allows JMAG to investigate phenomena beyond electromagnetics. With JMAG, you can simulate heat analyses, iron loss analyses, stress, sound pressure, vibration analysis, joule loss analyses, and electrical field analyses. The open interface also allows JMAG to work more closely with system and controller simulations. For example, you can take your high-fidelity motor model in JMAG and extract the performance parameters using JMAG's RT tool. JMAG RT can then be used to generate a block representing the electromagnetic device. This RT block includes all the nonlinearities in your model and can now be exported to other circuit and control simulation programs. This RT block is a completely independent block that functions in the controller domain and requires no interaction with the JMAG model. The RT block can be used in circuit simulators such as MATLAB Simulink and PSIM. It can also be used in 1D system simulation packages such as System Vision, Synopsys, MapleSim, and GT Suite. The RT block can also be incorporated into hardware-in-the-loop simulations from Opal RT, DSpace, and National Instruments. As you can see, the RT block allows you to cross multiple domains and generate high-fidelity system models. With the open interface, you can also work with thermal and structural FEA packages such as Dassault Systèmes Abaqus. Working with Abaqus, JMAG can use either one- or two-way coupling to export joule losses to a thermal model or electromagnetic forces to a structural simulation. With two-way coupling, you can now run a full co-simulation with JMAG and Abaqus. JMAG can also link with programs such as LMS's Virtual Lab to do noise simulations. In the example below, we take the electromagnetic forces from JMAG and then model their interaction with the modes of vibration, which are then calculated in JMAG or LMS's Virtual Lab. The interaction of the electromagnetic forces with the modes of vibration will result in noise that may be audible. The third category of JMAG advantages is high-speed processing. JMAG has many features that can reduce your analysis time. One of those features is the time-periodic explicit error correction function. This can force a transient model into steady-state operation more quickly than if the model is allowed to naturally achieve steady-state operation. If you are not concerned with the transient phase but only want to examine the steady state, the TP-EEC can help you. In this induction machine example, using the TP-EEC allows the simulation to reach steady-state operation 3 times faster than the standard analysis method. High-speed processing can also be achieved by improving the solver algorithms. JMAG uses an ICCG method for both 2D and 3D models. For the 2D models, on the left side, solver improvements have led to an 85% reduction in analysis time. For the 3D model on the right side, solver improvements have led to a 72% reduction in analysis time over the past 4 years. JMAG will continue to improve its solver algorithms, but you also have the option to use a parallel solver on multiple cores. Parallel solvers can dramatically reduce the analysis time of large models. In the example on the bottom of this slide, if the analysis on a single core is the baseline, running on 2 cores has a 2 times speedup rate. 4 cores will provide a 3 times speedup rate, and running on 8 cores in parallel will have a 3.5 times speedup rate as compared to running the analysis on that single core. JMAG can also work with your computer's hardware. We have been developing solvers that can utilize the computer's GPU to help speed up calculations. In this example, we will look at analysis time for a magnetic recording head. With a single CPU, an analysis takes nearly 200 seconds. But if we add the GPU, we can do the analysis in 120 seconds. At this stage in our development, however, we find that adding the GPU to a multiple core simulation does not create a significant improvement in analysis time. But we are still developing this approach, so I expect we will see improvements in this method in the future. The last main category of JMAG advantages is high productivity. One way to increase productivity is to generate visual results more quickly. In previous slides, we talked about JMAG RT and creating a lookup table that represents the device's performance. With JMAG RT Viewer, we can take that performance information and generate visual aids such as torque versus speed plots and efficiency maps. These visual aids can be viewed in JMAG, or the numerical data can be exported via CSV to programs such as Excel. High productivity also requires working efficiently. Most companies use CAD packages to create their solid models, so having to recreate the model for the FEA adds time to the analysis process. JMAG Designer can link directly with many CAD packages. This means that you can generate a geometry with your CAD program, import it to Designer, set the analysis conditions, and run the model. But now if you want to change a feature such as rotor thickness, you can modify the CAD model and then update the geometry in JMAG. Having this direct link eliminates the need to re-specify the analysis conditions on the new geometry and can reduce setup time substantially. The CAD link can also be used for parametric analyses. In this example, we are testing different gaps in a transformer to examine the self-inductance and flux distribution. In JMAG, you can set up the parameters for the parametric study, and JMAG will control the CAD geometry. Of course, you do not need to have a CAD link to perform a parametric analysis. Parametric studies can also be done through the geometry editor embedded in JMAG Designer. Many companies have requested tools to automatically generate geometries. Beside the standard motor and transformer templates, JMAG version 12 will introduce a winding generator. This will automatically create end-turns and geometries in JMAG Designer and allow you to examine the effects of these end-turns on your model in more detail. So we have seen some of the advantages of JMAG. Now let's take a look at some test cases demonstrating how you can use these features. JMAG's mesher can create symmetric mesh based on a model's periodicity. A symmetric mesh reduces mesh noise that can lead to error accumulation. In this example, you can apply the symmetric mesh to a model to generate a more accurate cogging torque. We discussed JMAG's comprehensive material database and how this is necessary to accurately predict performance. Another function in JMAG is the iron loss tool. We have found that the most accurate iron loss predictions are calculated as a post-processing function. With JMAG's iron loss tool, we have found very good agreement between measured losses and predicted losses. JMAG's version 12 will introduce a dynamic loss calculator as well. This will allow you to predict the effects of iron losses on output parameters such as torque and power. In another example, JMAG's winding template can generate end turns in a model which can then more accurately predict stray losses. JMAG Structural Solver can use the electromagnetic forces to predict noise and vibrations of motors. This makes it possible to ensure that a device's audible noise is within an acceptable range. The JMAG RT motor block has been incorporated into hardware-in-the-loop simulations from companies such as Opal RT. This allows you to test prototype electronic control units without connecting it to a physical motor. The virtual motor means that you can reduce the amount of test time on a dynamometer. It also allows you to simulate tests that would be destructive to the motor without destroying an actual motor. National Instruments has also implemented the RT block on FPGA chips. This means that they can run high-fidelity motor simulations at near real-time speeds. This works well for hardware-in-the-loop simulations, but also could lead to more advanced controller algorithms. For companies that develop large electromagnetic devices, you may have reduced the model complexity in order to achieve reasonable analysis times. JMAG's powerful mesh generation tools allows you to generate detailed part meshes to examine factors such as stray losses or saturation without having to run excessively long analyses. So in this example for the generator, you can see a very complex end-turn geometry that we're able to create a mesh in detail for this end-turn geometry and thus capture the stray losses that they would produce. At the same time, we're not sacrificing the analysis time, and we still have the capability to look at the internal flux density distribution and see where it fits on the BH curve. Using JMAG, it is also possible to investigate AC losses due to proximity effects. In this example, the primary and secondary coils are individually modeled to examine the non-uniform current distribution. This makes it possible to calculate joule losses, including the additional resistance created by proximity effects. For large power components, stray magnetic fields cannot be ignored. Some stray fields lead to eddy current losses, which reduce the overall system efficiency. Some users use JMAG to determine the location of excess eddy currents in surrounding components such as this IPB connection box. This allows them to generate designs that minimize the effects of stray fields and improve system efficiency. This example shows a high-frequency eddy current heating in a gear. This analysis relies on a multi-physics simulation of electromagnetic fields and thermal effects, but it also requires accurate material descriptions. Knowing the heat flow through a component can lead to better methods to evenly heat the teeth. Induction heating problems can also be simulated by coupling to programs such as Abaqus. In this example, we look at an induction cooker and how effectively it can heat a pan. We can also examine the stray fields being generated in the surrounding structural components to ensure that they do not get hot as well. JMAG can also be used to test bus bars. In this example, a current is applied to a bus bar with wire bonds. The resulting joule losses are captured and sent to a thermal simulation that can then look at the resulting temperature of the bus bar. Our last example shows a very complex simulation of a circuit breaker. The electromagnetic forces are simulated in JMAG, and using the MPCCI link, the results are exported to ANSYS's Fluent program to examine the fluid dynamics during the discharge. The MPCCI link is an option that allows us to connect to nearly any finite element package on the market today. In conclusion, the past 30 years have seen a great deal of improvements to JMAG, and we plan to continue improving JMAG's products and support. We strive to gain our customers' confidence through hard work and dedication. Based on customer feedback, we seek to provide innovative software solutions. I hope that you found today's presentation informative. We covered a lot of information, and typically we would end our webinars with a question and answer session. Unfortunately, today it would be easier to answer questions directly. I encourage anyone with a question to contact your local POWERSYS office. We're always happy to talk to you. Thank you again.